Is JP Chua, and today we will be going over the rates of change in trigonometric functions. So we have a question from page 371 in our Nelson Advanced Functions textbook, and it's question 9. So let's go over the question. The first question is determine an equation for a curve that models the ratio of mice per owl. So we have the graph here that shows the mice-owl ratio in the time in months, and it shows the relationship between the two in a trigonometric graph. So as we know, the equation for a graph is y equals a sine or cosine bx minus c plus d. A being our amplitude, b is our period, C is our phase shift, and D is our axes, or our vertical shift. So just by seeing all this, we can tell that we're in the trigonometric section of our textbook. So now we have to find this equation using this graph. So it gives us the maximum and minimum values already. So we can use that to find our amplitude. So our max value is 24.7 and our minimum value is 15.7. So that automatically gives us our amplitude. We subtract these two numbers and we get 9. And since we're using sine, we see that our axis is right here in the middle. So we have to divide that by 2 because the amplitude is that and that. So 9 divided by 2, our amplitude is 4.5. Next we go with our period, and we're going to start here at 16. So our period is, and the period goes to 40 right here. So 40 minus 16 equals 24. In order to find the b value, we do b equals 2 pi over the period. And since b is 24, we do 24 equals 2 pi over b, cross multiply, b equals 24, b equals 2 pi, and then you get b equals 2 pi over 24. And then our phase shift, since we started at time equals 16 months, that just means our c value equals 16. And our axes is our maximum or minimum value minus 4.5. And that equals 20.2. So if we put all this information together, our value is y, amplitude is 4.5, sine 2 pi over 24, x minus 16 plus 20.2. Then we have to use our next question. Use the curve to determine when the ratio of mice per owl has its fastest and slowest instantaneous rates of change. So we can use the graph to have a visual. If we start on the axis right here and we go up and up, we see that as we're going up closer to the axis, the rates of change would be faster, because as we get towards the maximum minimum values, it takes much longer to get there. So just using that information in that little visual, we can tell that our maximum and minimum points have our slowest rates of change, and our points on or near the axes have the fastest. And if we want to be really specific here, those points are in time, fastest are months 4, because it's on the axis there, months 16, months 28, and months 40. And those are all the time numbers on the axes, and the slowest in time are those of the minimum and maximum. So there we have 8, 22, 34, and 46. And those are all our months. And so now we're going to use that information plus this information to use this equation to determine, to estimate the instantaneous rate of change at its maximum. And so we use a centered interval of 1 month before to 1 month after. So basically what we have to do is we have to find the instantaneous rates of change. So we're going to use our equation, which is y equals 4.5 sine 2 pi over 24 x minus 16 plus 20.2. And the maximum, we're going to use this value here since it's given to us, is 22. But it wants 1 month before to 1 month after, so we can't use 22, so we're going to use 21 and 23. So that is our x value, and all we do to find the instantaneous rate of change is we plug the x value into the equation. So if we do that using our calculator, 4.5, so let's just start with 21 minus 16. We get 5, so we're going to plug in 2 pi divided by 24 times 5. We get that number right there, times 4.5 plus 20.2. And then we get 26.0905. And we always round to 4 decimal places, so we can be as accurate as possible. Now we're going to plug 23. So 23 minus 16 equals 7. So we're going to plug in 2 pi over 24 times 7. We're going to multiply that by 4.5 plus 20.2. And then we get 28.4467. And to find the instantaneous rate of change, it is our y values subtracted on top, and then our x values subtracted at the bottom. So we can do 28.4467 minus 26.0905 divided by 23 minus 21, and that gives us 28.4467 minus 26.0905, and that gives us 2.3562 divided by 2, and that gives us 1.1781. So therefore, our instantaneous rate of change, or IROC, is equal to 1.1781 at its max. So there, we've answered all our questions. This type of information can be used for biologists, as we're using mice-to-owl ratios. It shows us the different types of times and months that the two correspond with each other, and can use that information to help track them in the wild and things like that. So hopefully this video has helped us all understand how we can find information using graphs and equations to determine instantaneous rates of change, and I hope that we made it clear to everybody. So thank you.